Millions of years ago, Saturn has an extra moon. Perhaps 400 kilometers across and formed almost entirely of ice. But this moon is doomed. It's orbiting just too close to resist the immense forces of Saturn's gravity.
The rings probably formed from an object that got too close to Saturn. There's this invisible boundary around Saturn called the Roche limit, and that's the limit, depending on what you're made of, where Saturn's gravity is strong enough it will actually pull you apart, that the gravity on the side closer to Saturn is strong enough that, compared to the gravity on the other side, that will literally rip you apart. You don't have enough gravity of your own to stay together.
A leading theory suggests that just beyond Saturn's atmosphere, an ice moon approaches close to or even just inside its Roche limit. As Saturn's immense gravitational force pulls it apart, the moon begins to rupture catastrophically. A world ripped apart by its proximity to a giant. Up to 17,000 trillion tons of ice breaks apart in orbit around Saturn. And thanks to the speeds this material is traveling, it's likely that in just a few days, it spreads out to encircle the great giant. Saturn's iconic ring is now in place. But as Cassini turns its instruments towards it, it sees a single ring, transformed.
The images we returned, they were phenomenal. They were resolution a factor of maybe 20 times better than anything we had had before.
Cassini reveals how Saturn's giant rings have evolved. This debris now forms a disk wider than Jupiter, yet on average, just 10 meters thick. Within, moon-sized chunks of ice orbit the structure, clearing great voids, turning one ring into many. But it's as Cassini captures images with the sun directly above the equator that the most surprising feature of the rings emerges.
We knew this was going to be a time for us to investigate the third dimension, something that you don't get to see when you just look at a picture of Saturn's rings. And what we found was staggering. Just right out of the gate, we saw vertical structures. I just can't tell you how surprised we were to see this. It's just the spectacle of it was just unanticipated. I have just imagined flying along in a shuttlecraft across the ring, right, close to the ring. So to my perspective, it would be almost like it was an infinite sheet of gleaming debris. And I'm flying along and flying along and flying along, and suddenly I come upon a wall of rubble that's 2 miles high. I mean, is that cool or what? Really, I've said over and over again, they should put that in a movie.
This once tiny world of rock and ice that has seen the most dramatic transformations is today the solar system's greatest jewel. After more than a decade in orbit, Cassini has forever deepened our understanding of Saturn. But its mission is far from over.
Today, I am proud to announce that our next New Frontiers mission, Dragonfly.
So Dragonfly.
Go Dragonfly.
We're building a drone the size of a car, and we're going to fly it on a moon.
Dragonfly will explore Saturn's largest moon, Titan.
In 2027, Dragonfly will launch on its 872 million kilometer journey to Titan, the most Earth-like moon we've discovered so far. By the time Dragonfly's baseline mission is over, we'll have flown more than 100 miles, which is almost double the total distance covered by all of the Mars rovers combined. I'm a co-investigator on the Dragonfly mission, and I'm really looking forward to being able to see Titan through Dragonfly's eyes. Titan's been running a big experiment, and it's time for us to go collect the results. Titan is so amazing because in a lot of ways it's very Earth-like. It's the only moon in the solar system that has an atmosphere. It has rain, it has clouds, it has lakes and rivers and sand dunes and mountains. And so, big picture, Titan has all of the things that we think are required for life. We think that there was a period in Earth's history around the time when life originated, when Earth's atmospheric composition was actually probably quite similar to Titan's atmospheric composition today. And so, another one of the questions we have is, what was the chemistry like on the early Earth? How was it related to what's happening on Titan today? And what does that tell us about the origin of life on Earth? Titan is enshrouded in this kind of orangey yellow haze that keeps you from being able to see the surface. And so it was like, okay, we can't see the surface. It's the only moon in the solar system that has an atmosphere. And now we're finding out that there's all of these carbon-containing molecules in the atmosphere that are really, really interesting. And Titan is so interesting that we needed to know more about it. Titan is one of the best, if not the best place in the solar system to fly. If you personally were on Titan and you had some kind of wings attached to your arms for some reason, if you flapped your arms, you would actually be able to fly under your own power. It's that easy. And it's a combination of two things. One thing is that the gravity is pretty low on Titan. It's about 1/7 of the gravity on Earth. So that helps because you don't need as much, energy to get off of the ground. But the other reason why it's so easy to fly on Titan is that the atmosphere is actually more dense than it is at the surface of Earth. So it would be much, much easier, it is much, much easier, I think, to try to figure out a concept to fly on Titan versus trying to send a rover. Dragonfly is not a little backyard drone. It's about the size of a small car. And so that makes it, pretty robust to a lot of things that a backyard drone would not be robust to. Although if it crashes into a tree, as long as we know that it crashed into a tree on Titan, we will be super excited. We will call that a successful mission because we found life on Titan accidentally. We just don't know that much about the surface. And so on the one hand, that's scientifically exciting. And on the other hand, that's a little scary when you're an engineer that's trying to build a spacecraft where you can't, call AAA if something goes wrong. because of the time delay in light travel between Titan and Earth, the Dragonfly is going to have to navigate all on its own. There isn't going to be somebody, sitting on Earth with a joystick flying Dragonfly. There's no GPS at Titan. There's nothing to tell it where it is. Our maps that we have right now are not very good, and so kind of one of these a little bit like, build the plane as you're flying it type things in terms of how we navigate. And basically the way that it's going to be doing that is by taking a really, really lot of images. Where basically every time we fly, we're actually going to fly further than where we want to land so that we can do reconnaissance aerial imaging of the place we think we want to go next. And then we'll turn around and go back to where we had planned to land and land there. Once we tell it, okay, you're going to go do this thing, it will have the whole sequence of what it needs to do. It will be able to make decisions if something goes wrong, and it will decide, okay, this is what I'm doing now. And then, we'll report back and say, look, Mom, I did it. Hopefully. But there's definitely a lot of challenges involved in having these big time delays, because we can't control anything in real time. We have all these ideas about the requirements for life. And big picture, we tend to think of the requirements of life as a source of energy, building blocks of life, so like just things that are made out of carbon, and some type of liquid. We think that Titan is a place that it has the possibility of having life. Things that we know we have on Titan are a whole variety of what we call organic molecules. So one of the reasons why we're so excited about carbon when we're thinking about, the search for life and the origin of life is that, selfishly, life on Earth is based on a lot of carbon-containing molecules, and so that's one of the reasons why we're so excited about it. But actually, atomically, it's very interesting. Carbon can make 4 different bonds, whereas when you look at something like oxygen, which can really only make 1 bond or 2 bonds. If you think about your kids' Legos, you can only build so many things with a little like 1-piece Legos, but when you start using the 2 or the 3 or the 4 or whatever, you start to be able to build these really complicated things. And it's the same thing with carbon, because it can make these 4 bonds. It really allows it to make all of these different kinds of molecules, and we think that we see evidence of a lot of that going on in Titan's atmosphere. So we already have a bunch of different simple little Lego structures in the atmosphere, and we just want to know how complicated they got. And whether or not that is kind of similar to the level of complexity that we see on Earth, which might indicate the possibility for the presence of life. And so we want to go and see, with a actual Titan scale laboratory, what has formed from these processes. And so, the more opportunities we have to be able to explore places, the fewer limitations we have on answering our science questions, which is really important.
It was really a wow moment. There was liquid water elsewhere in the solar system. We had been right. You have all of the ingredients that you need, that we know of, to develop life as we know it.
We have cleared the tower, and the Cassini spacecraft is on its way to Saturn.
So these sort of hard cases, these James Bond-looking cases, are used to transport the flight hardware. This is one of the magnetometer sensors that I worked on, and it will have been integrated onto the boom that came out from the side of the spacecraft.
And here's part of the magnetometer instrument, and here's the other half of the magnetometer instrument. This is a quarter-size model, so this is a quarter-size me. I'd like to be this weight, not this height.
She was one of the best things about the Cassini mission, because I spoke to her on the phone every couple of days for years and years and years. So a gas giant like Saturn is incredibly mysterious.
Saturn just captivates people because it looks so supernatural. It engenders the immediate feeling that it can't possibly be real.
It has no solid surface, and it has rings around it, and we don't necessarily know where those rings came from or how old they are.
These, as you can see, are spiky shadows that are created by these features here that are sticking up 2.5 miles.
Having the perspective of Cassini to be able to see that was one of the most extraordinary things, I think, about the images that came back.
It was just extraordinary. It was out of science fiction.
Some of the most amazing discoveries that Cassini made were about Saturn's moons. The first flyby of Enceladus was not terribly close, but something funny was happening in the magnetometer data.
Okay, so put it into slideshow.
My boss came to the team and said,
You can see there's a little pimple in the data, just over there.
This looks intriguing. This is not what we expect. We expect on a rocky moon for the magnetic field to drape over it, a bit like a nice peaceful curtain draping over a window that's not moving. And instead, it looks like there's some sort of breeze gently fluttering that curtain.
And what we were able to do is calculate what ions were generating those waves, and it was water group ions.
So Michelle decided, after discussions with all of us, that she would go to the Jet Propulsion Lab and she would propose moving the next flyby of Enceladus, which wasn't for some time to come, to much sooner. And this was a huge risk for her.
We knew for us to be able to have a chance of really seeing what was going on at Enceladus, we needed to get closer.
The principal investigator of the magnetometer, God bless her, she went into action and convinced the project to take the spacecraft close to the South Pole so we could all get a better look.
And I must confess I didn't sleep for 2 or 3 nights before that close flyby, because if we hadn't seen anything, no one would ever have believed anything I said again. So, but what we found was spectacular.
This image made me nearly fall off my chair, because here we see dozens of jets, big and small, coming off the South Polar region.
It was fantastic. It was really a wow sort of a moment. There was liquid water elsewhere in the solar system other than the Earth. Enceladus, tiny rocky moon of Saturn, is geologically active. A stable liquid environment, organic material, and contact with rock, you have all of the ingredients that you need, that we know of, to develop life as we know it.
I love this picture, and it's about as much meaning as you can get out of the Cassini mission, because we know that that moon has an ocean in it that could harbor life.
One of the mysteries of Saturn originally was the source of the rings, and it turns out that Enceladus's geysers feed the very faint but very wide E-ring. It shouldn't be surprising that we found such interesting geological activity on a planet with 82 moons. Ironically, all these wonderful discoveries that we made meant you run out of fuel. It was on 1%. It had an empty tank, so we had to crash it into the planet and let it go.
This is the start of the end of the mission. We're running out of fuel, and we're going to make sure we go out with as much great science as we can.
We want to see how much of the atmosphere we can see before we lose the signal, before it can't fight the atmosphere anymore and it goes off point.
These last grand finale orbits where Cassini dove between the rings and the planet, they were never foreseen in the original mission planning. Actually getting to do that was really remarkable. Take these kind of dangerous dives between the rings and the planet to see what that space was like, actually with the spacecraft physically being there, was really remarkable.
In some ways, I just want it to be over now. You know, you're sort of waiting for it to end, and it's really weird.
Quite a lot of us were gathered round, tensely waiting for the data to come back. We were relying on the commands that we had written and we had sent to the spacecraft to have worked properly, and for the spacecraft to continue to be able to talk to us right up to the very last minute.
I can confirm science playback is locked.
And then it'll go away. We'll lose the signal, and that'll be end of mission.
Cross for 0 time.
So that would be the end of the spacecraft. Project manager off the net.
It doesn't feel a long way away, actually, because every time I watch it, I am immediately there again. So that I guess says something about the impact that the end of mission had.
That was a great spacecraft. It did exactly what we asked it to do, all the way to the end.
When you have checked on a spacecraft every day for more than a decade, and then suddenly it's not there, it really is a wrench. It's a blow, and you feel sadness and a certain amount of grief.
Godspeed, think it and release it.
This is the Matanuska Glacier in Alaska. It really is one of the most astonishing places I've ever seen. And this whole landscape is testament to the erosive power of this stuff, this mixture of ice and rock as it rolls down this valley over hundreds of thousands of years and creates this astonishing landscape. But the reason it can do that is because of the delicate balance of the Earth's atmosphere. See, our planet is just at the right temperature and pressure to allow water to exist as solid, as liquid, and as gas, as vapour in the clouds. And so the sun can heat up the oceans and it can move the water over to the top of the mountains. It can fall as rain, turn to ice, become a glacier, and then sweep down the valley to sculpt this astonishing landscape.
Just as our atmosphere allows all this to exist, the atmosphere of Titan is the perfect temperature and pressure to allow something to exist that has never been seen before on a world beyond Earth.
This is a picture taken of the South Pole of Titan by Cassini in June 2005, and it's subsequently become one of the most important and fascinating pictures in the history of space exploration. The interesting thing is this black blob here. Now this fascinated the Cassini scientists, but the explanation as to what that is had to wait just over a year till July 2006 when this picture was taken. And it's a radar image, this time of the North Pole of Titan. And you see again these huge black areas. But black in this case means that the radar waves that bounced onto them didn't come back, so they're completely black. And there's only one really good explanation for that. That is that they're incredibly flat surfaces. In fact, they're surfaces of liquid. So this picture combined with this picture means that this is the first observation of a liquid, a lake, on the surface of a body other than the Earth in the solar system. But these lakes, of course, cannot be lakes of liquid water because the surface temperature on Titan is minus 180 degrees Celsius. And at those temperatures, water is frozen as hard as steel. So if these are not lakes of water, then what are they?